please, then. How about if we actually, I mean, there was too much confusion, so I want to solve the quiz on the whiteboard. I saw that some of you were really confused about what things over there really mean. All right, so this is approximately what was the picture on the quiz, and F, and I see that some of you were trying to place a mirror somewhere. I mean, I saw that people put mirror here. Why? Now, what does this thing mean? C. Center of what? Of the curvature of the mirror, right? So obviously, if this is the center of the curvature of the mirror cannot be here. All right? This is the center of the sphere. Now, this is a focal point. Well, the distance from the center of the mirror to the mirror is twice as big as distance from the focal point to the mirror. So, if you don't see the mirror on this picture, where it should be? Well, the same distance as this distance, which means that this was the mirror already. This was not the object for which you had to find an image. So here is the mirror, and here is the object. Well, now, I saw that most of you actually were able to trace chief ray properly. Chief ray is relatively simple to trace. And so here we have the point where principal axis crosses the mirror. So how about if we do it in color? So light coming out from this point, traveling toward the mirror. This is along the chief ray, will be reflected symmetrically. And it will be reflected. So the arrow should be away from the mirror. Now, some of you used parallel ray. Some of you used a focal ray as the second. And in principle, two rays are sufficient. And if you draw all four rays, then the picture becomes a little bit messy. So I really suggest that you draw just trace two rays, and imagine a third one for the checkup. I will draw, however, all three here. So let's start with the object parallel ray. And so parallel ray is parallel to the principal axis. Sometimes it is also called paraxial. Well, the mirror is too short here. You have to imagine that you can extend that mirror appropriately. And, well, in principle, it is curved, but you won't make the error will be insignificant if you just extend it as a straight line. Actually, the difference between that curved surface, if you draw a ray diagram, and straight line is the evidence of the spherical aberration. All right, so now, again, object ray travels toward the element, and when it is reflected, it becomes a focal ray, image focal ray. So it is reflected from the mirror toward the focal point. Well, we see that the rays themselves won't cross each other, which means that their extensions have to cross. So if I continue the extensions, I find that here is the image. And it is behind the mirror, so obviously light doesn't travel there. The image is therefore virtual. Now, some of you actually used also object focal ray. Also, object focal ray is a ray which the ray or its extension will pass through the focal point. So it means that this is focal ray. And after reflection, focal ray becomes parallel to the principal axis. As if I make an extension, I can see that all those three rays appear to originate from the point over here. So here we have the image. As the last exercise for the mirrors, I want to give the most difficult task of because when you think about it, so far we in our exercises we put a mirror somewhere and so what will happen. This is not usually what we try to achieve whenever we construct something. When we construct something, and it doesn't matter if it is optical element or a car, we want to assemble pieces of nature in such a way that it is going to perform a particular task, right? So let's put it that way. It means that I want to take an object and place somewhere, and I want to get an image somewhere, like over here, for example. This is, however, with the lens, but look at that. We wanted to have a projector placed over there. And it is supposed to project a slide which is displayed on the screen in the projector. So that display is somewhere over there in this box. We want now to have image of that screen, tiny screen inside in this plane so that we can observe over here. So now the task is where and how to, and what type of a lens to place so that from the object over there I'm going to get an image over here. And why don't you actually even come up with a task? So let's say that I'll just draw the principal axis on which we want to have things, and come with an idea where would you like to place an object. It's up to you. We'll come up with the solution later on. So let's put object on the right side, erect or upside down? Okay, so object is here. Yeah, and from this object we want to get an image somewhere. Suggest where you want and how. Anything will work. I mean, we can come up with a really crazy arrangement and then figure out how to achieve it. Yes, go ahead.
Image right up right on top of the object.
Right on top of the object, over here, but the other way, right? Now, how big? 50% of this one, okay. I like actually. I mean, we are really quite malicious, but that's okay. Because this is possibility of a design. Andrew wants to have image of this point over here. Okay, where we should put the mirror and what should be the, I mean, what type of a mirror we should take. I advise you to start with the chief ray. Think how the chief ray is supposed to travel. Maybe actually before we let's come back to this. Let's find the simpler configuration. Andrew, come with the simpler configuration. So, because I like this configuration though very much.
On the same side, somewhere off to the left. Back
To the left.
yeah.
How big?
That's the same size as the other one.
About. Yeah, so let's make it about this big. About this big. So Andrew wants to have an image here. Well, the first thing is, well, can we trace at least one ray? Yeah, and which ray would be able to trace? Actually, I'll tell you which one is the easiest and is the only one which you be able to trace. Is the start with the image chief ray. We can trace image chief ray from this information. So for a moment, I will remove that malicious one. Yeah. Now, right now, we don't even know if the rays are supposed to travel to the left or to the right. Now, I know one thing. I suggested to start with chief ray, image chief ray. I know that the image chief ray goes through one of the points which is marked on the whiteboard. Which one? Image chief ray. Now you look over here. It's what? No, it's not going to be parallel to principal axis. Well, the only point for which we know that it is going to, which it is going to pass at this moment is this point. All image rays have to pass through this point. Well, by having one point, we don't know how to draw a line. However, we know that the image chief ray passes symmetrically through object chief ray. Now, and the principal axis is the axis of symmetry. Well, object chief ray passes through this point. Object chief ray passes through this point, which means that image chief ray passes through a point which is symmetrical to this one. So it passes through this point, right? I already have 2 points through which I know that image chief ray is passing through. I can draw the line now. Chief ray is a straight line. Close enough. What's my conclusion from that? Adam, Andrew, do you have a conclusion?
Well, the image should be virtual based on that.
From that, Andrew concluded that image is virtual, which is true, but actually in order to make this conclusion, he made another conclusion earlier. He already recognized where the mirror is supposed to be, right? Where? Where the chief ray crosses the principal axis. So the mirror has to be here. This is where the mirror is supposed to be. Now this is image chief ray. Well, here we have the object, although in principle I didn't specify if object is virtual or real. So let's say that this is a real object. If it is a real object, then light is coming out from here, travels toward the mirror, and it is reflected that way. If it is virtual object, it means that light is traveling from this direction, and it is reflected that way. So which one do you want to have, real or virtual object? It doesn't matter. Pick one, Robert. Virtual. Okay, so let's draw the ray diagram for a virtual object. So I will cross it, mark that it's like that, which means that the rays are converging to this point. So this is object chief ray. This is object chief ray, and this is image chief ray. So actually, if the request from Robert and from Andrew exclude each other, because in this situation, if it is a virtual object, we see that the light is passing through this point, so it is going to be a real image. All right, so we have already figured out where to place the mirror. Now, what mirror? Well, what type of a mirror is identified by the focal length. So we have to now determine where should the focal point of this mirror be in order to produce this image. So give me suggestion, and actually you can have two solutions now. Two solutions would work. Well, definitely we will need to somehow to trace a focal ray. And it happens that no matter if I take object focal ray or image focal ray, it is going to cross the principal axis at the focal point. So I have to draw rays which will require from me to mark the focal. Right, a parallel. Yeah, so let's start with a parallel ray. And which one would you like, Robert? Object parallel ray or image parallel ray? Let's take object parallel ray. So object parallel ray. This is object parallel ray. So I recognize that it hits the mirror over here. So where the, now after being reflected, how it is going to be reflected? toward the focal point, but I don't know where the focal point is. However, I also know that it has to pass through the image point, which means that it is going to be reflected this way. So where is the focal point? Further away, right? We'll have to continue. And when this focal ray crosses the principal axis, focal point is located. All right, so now looking at this diagram, what kind of a mirror it is? I know already that focal point has to be here. Yeah, light is coming from this direction. It is reflected in this direction. Focal point is here, which means that it is a concave or convex. Who votes for concave? Who votes for convex? Those of you who voted for concave, you were right. Yeah, the reflecting surface is on the left-hand side of the mirror, and the focal point is in front of the mirror, which means that it is a concave mirror. All right, let's now try. What do you say? Right, I know what you mean. If it was a real object here. Sorry, I'm sorry that I deleted it. Yeah, let's see what will happen. All right, so Robert asked what will, how the diagram would be different if we had real object here. Well, if we had real object here, it means that the light will be traveling the other way. So now, this would be wrong here. Here it would be a continuous line. Light will travel this way, will be reflected that way, and parallel ray would travel this way and will be reflected that way. So these lines would be broken. I don't even need this one. And so now the extensions of the rays form the image. This image is therefore behind of the mirror. Now the mirror has to be on the other side. Like light is traveling from this side, reflected that side. Mirror focal point now is behind the mirror, which means that focal length is negative, and this time the mirror is convex. All right, let's now go to the original arrangement. So this was object, this is image. And how about if we ask Andrew how to do it?
Well, we're going to start with the chief ray again because
Okay,
it's the only one we know we can
let's
draw.
try with the chief ray, which means about image chief ray, right?
Yeah.
Yes, so I know that image chief ray has to pass through this point, and it has to pass also through a point which is symmetrical to this one. Yes, it has to pass through these 2 points. And, well, where chief ray crosses principal axis, this is where we're supposed to place the mirror. And so just looking at this this ray, using this one ray, I can recognize that the mirror has to be here. And then what? Now, what did we do after we placed the mirror? Yeah, because now everything agrees. Yeah, so we place a mirror over here, and chief ray coming out from this point hits the mirror over here and continues there. This is how the chief ray is supposed to travel on this ray diagram. I mean, how it should be traced, not travel, because the rays don't travel. I mean, the ray is a line. Now, then in order to determine the focal point, we decided to draw a parallel ray, right? So let's draw image parallel ray. Image parallel ray is like that. So it hits the mirror at this point, and now image parallel ray results from object focal ray. So ray from object has to hit a mirror over there after passing through the focal point. So where the focal point is?
Center.
Here. All right. So we have a mirror, such a mirror that the focal point is on the surface of the mirror. What is the shape of that mirror? You say?
Plane mirror.
I mean, you can imagine that it means that you have that the radius is twice as big as the focal length. Yeah, focal length over here would be how much? 0. Okay, so what should be the radius of the mirror? 0. Make it. You won't be able to make it. Yeah, you cannot make a mirror of 0 radius. And on top of it, you have to take a fragment of the surface. So the answer, yeah, I mean, why did I like this? Why did I like this problem? Because the answer is it's impossible. Yes, it's impossible. However, I like also the other suggestion. I know I didn't before I really asked Andrew to be more specific. I think that he meant to put an identical arrow. I mean, an arrow which is symmetrical. Let's try to solve this problem the same way. Andrew, can you give me a suggestion? Then which rate what should I use?
Follow the same procedure.
Following the procedure, we should start with the
chief ray.
Chief ray. Okay, I know that chief ray is supposed to pass through this point and through a point which is symmetrical to this one. And it happens that this point is symmetrical to this one. So the 2 points overlap, right? It has to pass through this point and through this point. Now this time I can draw chief ray. How? Oscar, how would I draw a ray now? Anyway, yeah, so I can draw it, let's say, this way. Well, it means that the mirror is supposed to be here. Object chief ray should be traced this way. I'm switching from blue to green. So object rays are green. Now I'll take a parallel ray, object parallel ray, hits the mirror here, should be reflected toward the image. Focal point is here. However, I could do it that way. How about if I do it with black? Oh, even this way. What's the answer?
Any of them.
Any of them will work. However, not exactly any. There is a certain constraint of the mirror. Yes, Robert?
Is it sitting on C?
It's what?
Is it sitting on the center of the radius of the mirror?
It doesn't matter. This doesn't matter. Now, the important thing is where the focal, I mean, what kind of what is the focal length? What can you say about focal length? Because it isn't any mirror. It has to be a concave mirror. Now that the focal point has to be on the same side as the light is coming, so on the reflective side. So we will have to use any convex mirror will do the trick will produce a symmetrical image. It will be the matter where to place it only. All right. Now I want to talk about another type of an optical element, which is used also to form images quite widely, because in mirrors, we use which phenomenon to create images? It's reflection. We can do the same thing using refraction. And well, with a good approximation, actually, if I take piece of refractive material and make the side surfaces to be part of a sphere, we will get something. We will get an element, optical element, which is referred as a thin spherical lens, and the thin spherical lens is also capable of producing images. Now, thin means that the thickness of the lens is small compared to its diameter. All right, let's now see how a lens works. In case of a lens, we can easily trace only 3 rays rather than 4. And the 3 rays are, lens also has such a property that the rays which originate from a point will meet at a point after refraction. Well, they will meet approximately at a point after refraction, and there will be 2 reasons for this approximation. One is the shape of the surfaces, and this failure associated with the shape, fact that that the surfaces are parts of spheres, are referred to as spherical aberration. Lenses have one more problem than mirrors, and that other problem is this dispersive property of material. Different wavelengths are refracted differently. So what lenses do, they split images into rainbow colors. And this type of aberration is referred to as chromatic aberration. So mirrors have only spherical aberration. Lenses have both spherical aberration and chromatic aberration. All right. Now, there is a certain complication which actually confuses students. It is that lenses have 2 focal points rather than 1. And the most common problem is to confuse focal points. Focal points are placed symmetrically. However, I want you to distinguish And I want to add this to the name of a focal point. You have to identify which one is so-called object focal point and which one is the image focal point. Make distinctions. You can think also that you have two focal points in case of mirrors, however they overlap. And the three rays which we can trace are the chief ray. And chief ray is even easier to trace in case of a lens than in case of a mirror, because chief ray passes, well, it's the ray which hits the lens at the principal axis, and it is continuing in the same direction. So image chief ray is an extension of object chief ray. It's a straight line passing through the lens. Now, the ray which passes through the object focal point is referred to as object focal ray. But it has to pass through the object focal point. If I take an object ray which passes through the image focal point, it's a random ray. We don't know how to trace it. We have to take object focal ray and trace, and it is going to be object focal ray if it is traced through the object focal point. And similarly, like in case of a mirror, this time, however, that after refraction, the light will travel along a ray which is parallel to the principal axis. So we will get image parallel ray. And the last one is the object parallel ray. Object parallel ray after refraction will pass through the image focal point. Now, it is also, sometimes it's a case that extensions, so either the rays or extensions have to pass through the focal point. So these are the three rays which we are able to trace for a lens. And they, in what sense equal? The distances are equal, correct. Yes, so focal length says how far are the distances. Now, for a converging lens, object focal point is on the side of object rays, image focal point is on the side of image rays, where the light really travels, and the focal length is positive. For a diverging lens, object focal point is on the other side of the lens than the light is coming from. And also the image focal point is on the other side than the refracted rays are traveling. We will exercise this on Monday. Now this selection actually of how we assign focal lengths and also positions of object or component of position on object and image makes the equation relating the positions and focal lengths in a formula which is identical to the mirror equation. So thin lens equation is identical to mirror equation, however the meanings are different. Now let's derive it. So let's say that the focal distance from the focal point to the lens, well, it identifies focal length and the distance, it doesn't matter which focal point I choose. However, since I drew a ray diagram over here using chief ray and object focal ray and image, object parallel ray and image focal ray, this distance is now more important. So let's say that component of position of the object is S, and if the object is on the side of the light, we assign positive value for position of the object. Now for images, if the image is on the same side as the image as the refracted light travels, then we assign positive value to position of the image. So in this configuration now here, both S and S prime are positive numbers, and F is a positive number as well. Image focal point is on the side of image rays. All right, I can now do a very similar consideration like for a mirror, and identify similar triangles and write appropriate proportions. So I can recognize that these two triangles are similar. So now the vertical component of positions are related to the horizontal component of positions of object and image. And we can recognize that this length over this length is supposed to be equal to this length divided by this length. Now, because the image is inverted, so this value h prime is negative, so the length is minus this negative number. Well, I can find another pair of similar triangles, these two. And now I can recognize that this height is also h. So this quotient now is equal to this distance, which is focal length, divided by this distance. And this distance is position of the image minus focal length. So I got it. And really now I have that position of the object, position of the image, and focal length are related. I can now just simplify it and eventually get to the same form of an equation as for a mirror. Let me just add one slide which says how, and I'm not going to derive it, but I just want you to memorize the relationship between shape of the lens and the focal length. So if I consider now the curvatures of both surfaces, and if the center of curvature is on the left-hand side of the surface, we assign a positive value for the radius of curvature. If it is on the right-hand side of the surface, we assign a negative value for the radius of curvature. And radii of curvature and indices of refraction of the material from which the lens is made and surrounding determine the focal length of the lens. So, for example, if I take a glass as the refractive material and make, let's say, double convex lens, in air, this lens is going to be converging. Focal length will be a positive number. However, if I make a bubble of air like that and dip it underwater, the lens will be diverging. Focal length is going to be negative. All right. So I think this will be all for today.